Okay, so I remember this altitude QS here divides that right triangle into two similar right triangles that is also similar, to the big triangle. So if you can find your corresponding parts, you can redraw all three triangles and then just write proportions with corresponding parts. And then, because that is hard for me, but I think I may have figured out an easier way to see that. Because of that, then there are two theorems, and those are what I always used to use to get the proportion right. So let's see if I can do this. So if I separate these triangles, I have the big triangle, RQP. Okay, so now I'm going to draw these other two triangles oriented the same way. So, let me try this one. P has to, of course, correspond with P. Since Q is the right angle on this QSP triangle, that makes S the right angle, which means this has to be Q up here. Okay, so far so good. Then I have this RQS triangle. Okay, and again, R has to correspond with R, so I'll put that there. And the right angle again is S, which means this must be Q. Okay, so then I'm going to put my numbers on. RS is 3. And if RP is 9, that makes SP 6. Right there. And then RQ is Y, which I assume is what they want us to find. So, let's see. Well, this is... What can I compare? Okay, so it seems if I compare the length of the hypotenuses of RPQ, so RPQ and RQS, oh, RQ's Y. I got it now. There we go. So we're going to compare these two. This one and this one, because we have a leg and a leg, and we have Z hypotenuse and Z hypotenuse. And lucky for us, that's going to create a geometric mean, which means we're going to be able to solve. Okay, so sometimes it's easier if you label. So I'm going to compare, the hypotenuse, hypotenuse to the leg. And then sometimes I make the kids do a little box and then like big triangle to small triangle, but I think we can do it this way. Okay, the hypotenuse of RQP is 9, and the leg is Y, which is proportional because they're similar to the hypotenuse of RSQ, which happens to be Y, and RS, which is 3. Okay, so now we have a proportion, so find the cross products. So therefore, Y squared is 27, and Y is going to be the square root of, well, that's ugly, the square root of 27. Okay, and then I don't know if you've simplified radicals yet, but that's what I'm going to do. So 27 is the square root of 9 times 3. The square root of 9 is 3. Square roots of 3. 3 stays in. Okay, so that's one way to do it. Here, I'll do another example like that, and then we'll look at theorems. So let me find a problem. I'm using my old textbook that I kept when I taught geometry. Okay, so let's see, what if we have, let me see, what did we not have there in that example? Did we not have the altitude? No, so let me do one where they give us the altitude. Let's try this one. Oh, and of course we have the triangle oriented a different way, because why not, It's not hard enough as it is. Okay, 18, 12, and Y. Oh, and of course we have no letters. This makes it a little bit difficult for me to like get the corresponding parts right. So I'm going to give this letters, and I'm going to use good old A, B, C, and D. All right. So if I draw a triangle the way I like to look at them, this way, the right angle's B, and I'm just going to put A here and C here because I think it will work. I know my right angle's D, and C has to correspond with C, which means this has to be B. Yes, maybe we are right. And then again, the right angle's D, and what am I looking at? A, B, D, A, D, B. So A has to correspond with A, so that must be B. All right, now let's see if I can get my numbers on here. BD is 18. So I have a BD there, and I have a DB, BD, whatever here. DC is Y. I've got that DC. And AD is 12. Oh, I was getting excited. I thought I might have to do 12 plus Y, which you could do, but I don't know why you'd really want to do that. That'll make things more complicated. But I suppose there is a time where you might have an expression that you have to square or multiply. You know, like this would, you'd have to write this as 12 plus Y. I guess that could happen, but not in this case, because in this case we have a leg, a corresponding leg, and then we have the other corresponding leg here, and life is good. And we can just write proportion like in, I don't know, we write proportions in, I think, 7th grade here. All right, so again, I'm going to compare leg to leg, and sometimes even tell the kids you can write down side and bottom, or hey, let's use good math language. We have the height, and we're going to compare that to the base of these right triangles. Okay, so the height of BDC is 18, and the base is Y, which has to be equal because they're proportional, because they're similar figures, to the height of ADB, which is 12, and then DB, which is 18. So this theorem says that, let's see, 18 is the altitude. So it says the altitude of the right triangle is a geometric mean, so that means it's going to be diagonal from each other in your proportion to the different parts of the hypotenuse. So to the different parts, to the segments of the line segment that it's perpendicular to, which happens to be the hypotenuse of the big triangle. So that one I remember. So the altitude, you take your altitude, you plug it in diagonal, and then in the other two diagonals you put the two pieces of the hypotenuse or the two pieces of the base that the altitude is a right angle to. Oh, see, it's coming back to me. That's how I always did it, because doing these triangles, I don't know, it was really hard for me. Now, some of my kids were like, oh, you just look at the similar figures. I'm like, yeah, whatever. Okay, so 18 squared equals 12y, and 18 squared is like 306, no, something has to end in 4. Hang on, let me just do real quick, because I have no idea where my phone is. So that's 4. Uncle Adam and I just looked at how to square numbers easily, but I can't remember 324. That's right, I knew that. So 324 equals 12y, and then we just divide by the 12, and you get your answer, which I'm going to look here in my book. Should be 27, they say. There you go. Okay, so that brings us to that theorem, which they call, do they call it the altitude theorem? Seems odd. I know there's a hypotenuse theorem and a leg theorem. They call that one the, why not call it the geometric mean altitude theorem? Okay, so who knew? That's what I love about mathematicians. We just call things what they are, usually. So the geometric mean altitude altitude theorem. Okay, and that says because you have the right triangles, and I suppose we could go prove it if we wanted to. What we just did, we proved by induction because you do a whole bunch of examples, and it turns out that to find the altitude, no, I did not spell that right. The altitude is the geometric mean, so that means it's going to be on the diagonal from each other in your proportion of the segments. I guess we'll use better language than pieces, than the segments of the hypotenuse of the same triangle the altitude is drawn to, right? Of the segments of the hypotenuse. So, I'll just draw a triangle this way. So if I call this A for altitude, I need to draw bigger so I can write bigger. I just write with my fingers, so sometimes that's why it looks messier than usual. Sure, we'll go with that. So that's the altitude. That means if this is B and this is C, that means you do this. Those are diagonal, B and C. So the altitude will be the square root of the product of the pieces of the hypotenuse. Okay, but at least that way you get your proportion set up right. And once you have your proportion, then you should be home free. Okay, so now let's look at this other theorem, which talks about the geometric leg theorem. So let me find another problem to solve where we're looking for a leg. And we'll see if we can make this. No, those are altitudes. Oh, my glasses are on top of my head. Okay, so I have this right triangle with an altitude drawn, but we don't know the length of that, but I know that that piece is 2, and this whole thing is 8. So I know that that piece is 6, and I'm looking for this leg over here on this larger triangle. Okay, so if I draw these, I'm going to label these again. A, B, C, D. And I think this is what's going to happen. This leg, AB, is going to be the geometric mean of the whole hypotenuse, 8, and the piece that's adjacent to it, 6. Okay, but let's see if that works out. Pretty sure that's how this works. It's all coming back to me. This is fun. Okay, B, A, C. And then we have 2 smaller right triangles, and the right angle for those is B. So I'm going to put that in there. And the A has to correspond to A, which makes this... No, that's not the right angle. Oy, oy, oy. Just when I thought I was having fun. Sorry. The right angle for those is D. Okay, so A has to correspond to A, so this is ADB. And C has to correspond to C, so this is CD. That makes that B. Let's put our numbers on and see if that's the right way the theorem works. So AC is 8, AB is X, AB is X, and what else do I know? AD is 6. And yes, I know that DC is 2, but I don't care because that's the only information I have on that triangle. So I don't even care about this triangle over here. Okay, so if I look at this and I am comparing my legs to my hypotenuses, hypotenusae? No, no. So I'm going to compare a leg to hypotenuse. And that is going to give me x over 8 equals 6 over x. And yep, the leg is a geometric mean of the entire hypotenuse and the piece that's adjacent to the leg you're looking for. All right, so x squared equals 48. Yes, we know this part, right? X is square root 48. Ooh, and 48 has some perfect squares in it, so we can simplify that rational. let's see, what is that, 12 times 4 or 16 times 3, right? So x is 4 square roots of 3. Or what do they say? They give me about 6.9, 4 times 1.7. Yeah, I guess that's about right. Okay, so let's summarize this theorem. This one is called the geometric leg. I guess it's called geometric mean leg theorem. Yes, means in there, leg theorem. And so that states that the leg is the geometric mean, so it goes diagonal from each other in the proportion of the, and again, I think we're talking about the pieces that are on the triangle that you're looking for the leg for, the big triangle. The leg is a geometric mean of the hypotenuse of the triangle and the segment or piece of the hypotenuse adjacent to or touching, to the leg that you're trying to find. Okay, that you're trying to find. Okay, so let's do one more using the theorem. Okay, so let me find an example here. Oh, what is a good one? That's an altitude. Oh, here's a leg. So I am going to be looking for this leg. That's a right angle. That's the altitude, so that's a right angle. And this is 4, and this is 5. Okay, so we know that the leg is the geometric mean, so it goes like that. You can put it the other way too if you want, but I always kind of start with what I'm looking for. So you can write it like this if you want to be all backwards and stuff. No, it's okay. It doesn't matter which way you write it. Okay, so the leg is a geometric mean of this entire hypotenuse, which is 9, and the piece that's touching this leg, so 5. So x squared is square root 45. So x squared is 45. So x, minor little technicality here, x is the square root of 45. And so that's 9 times 5, so 3 root 5. And then you could get your calculator. Okay, so let me know if you still have questions. I'm just looking to see what kind of weirdness happens. Oh, here's one. Let's do one where the piece of the leg is an expression. Yes, sounds like fun. Because, it's all easy. And then they throw, like, x plus 3 instead of a number in. And you're like, what? So let's just make sure. Let's see. I have drawn my triangle the wrong way. Hang on. I gotta make it match the book, or I won't get the numbers on right necessarily. Just kidding. Let's try again. They've drawn this way. Craziness. All right, so the altitude then is 6, and this piece is b plus 3, because we can't just have a number. Where would the fun be there? We have to have the algebra in the geometry. All right, and so we are looking for this piece of the leg. But I have an altitude, and I know that the altitude is a geometric mean of the pieces of the legs. So this works out nicely. Okay, so the altitude is the geometric mean of the leg pieces. So you're just going to stick that in there. You could put letters on this triangle if that helps. So, A, B, C, D. That's what I always use. You could all be creative if you want to. And then just remember your right angles correspond, and then A has to correspond to A. So that's a way to get those in the right spot if you are like me and can't just see it turning around in your head. I cannot do that. All right, 6 times 6 is 36. And then we need to do 8 times quantity b plus 3. So we get to do some good old-fashioned algebra. And so subtract 24 from both sides, or I always say, I want this over here, so now it's negative, because once it crosses the sign, it becomes negative. I had a kid tell me once, oh, like when you cross the border, you become a new man. I was like, oh, my Lord, sure. That's how you want to remember it. So 12 equals 8b divided by 8, and then b is 12/8, which is 4. Nope, just kidding. 3 halves. Where's my eraser? 4 goes into 12 3 times. There you go. Sometimes it's the simple math that gets me. Okay, or 1.5. All right, so if you have questions, let me know, and then we can go over some on the phone. Like if you have specific examples that you want help with, we can do those this evening when you have time. Okay, have ye a good day off. I'm going to get ready and go to stupid, boring workshops all day. Okay, love you.